topic is we are going to see the different variants of Turing machine. So I also suggest you to please try designing a Turing machine for this case. So we are going to try designing a Turing machine. Please design a Turing machine. Do this as homework. So design a Turing machine that accepts a palindrome. Okay, that accepts a palindrome over the alphabet of any strings that has A, B occurring plus one or more times. Okay, for example, if you have ABB, BBA, the reverse is also the same. So, okay, so any language like this. These are sample strings. So design a Turing machine that accepts a palindrome. So you should know when to stop and when to check. So please try to do this. Okay. Right. Now we are going to see two more variants of Turing machine today. One is like multi-tape Turing machine. Okay. Multi-tape Turing machine. So till now, whatever we have seen in the previous examples, I had one tape with me, one input tape with me. Okay. So it is similar to the memory in our digital computers. So it has a string. The string is sandwiched between blanks. Okay. So I know where to start. It can grow infinitely at both the ends. So this is my tape, but I have only one tape with me. Now there is a variant where I can have multiple tapes, not a single tape. I can have multiple tapes with me. Now when I have multiple tapes, each tape, say n tapes I am having. Okay, so n tapes, n input tapes are given to you. Okay, n input tapes are given to you. So in that case, each tape will have, what will each tape do? Each tape, you can access each tape with its own read-write head. Okay, with its own read-write, it will have its own read-write head. Okay, and this read-write head is controlled independently. It doesn't depend upon the other tapes. Okay, it's controlled independently. So these are the two things that we know. If you remember, we would have used multiple stack for this non-deterministic PDA. If you have remember, WWR, the same palindrome, even palindrome. The same thing, when we designed a push-down automata, we would have used multiple copies of stack. If you're remembering, we would have taken multiple copies of stack for push-down automata, right? And we would have managed, we would have seen like in one of the stack, if the stack symbol, if we reach the final expected stack symbol, then we would have accepted it, right? So this is something similar to that. So each tape will have its own read-write head and it will be controlled independently. So when we write the delta transition function, so this is the formal notation for Turing machine, if you remember, set of states, alphabets, these are the tape symbols, transition function, initial state and accepting state. This is the formal definition for Turing machine. Now delta, generally what you for a normal machine, a delta is defined as Q, the state Q on seeing a tape symbol. Okay, delta takes two inputs, state and the tape symbol. It gives the output of, there'll be a state change, there'll be a symbol rewrite in the tape. Okay, so we say it's crossed. So there'll be a state change, there'll be a symbol rewrite on the tape, and there'll be what? Movement of left or right, right? So there'll be movement of left or right. So this is a normal Turing machine. Okay, so this is a normal or single tape Turing machine, standard Turing machine. Okay, so for a multi-tape Turing machine, the same thing. You have to handle, listen, the control unit, we have only one control unit. Only the tapes, we have multiple tapes. Okay, so I'll have n tape symbols. So when there are n tapes, each tape, the head will be pointing to, its own head will be pointing to one symbol. Okay, so I have to write transition functions for everything. So Q, I'm in a state Q, and each tape symbol, each tape is pointing to which symbol I should say, and I should define a movement for each of the n tapes. Okay, so this is for multi-tape. This transition function definition is for multi-tape. Now let us consider an example of two tapes. I can have an example example of n is equal to 2. I'll have 2 tapes with me. Okay. So not example, normal Turing machine. How do I write the transition function? For example, I say delta, I'm the state Q0. When I see A as a tape symbol, okay, move to state Q1, replace A with say B and move left or right. Okay, so this is a normal transition function. Now, let us say it's a multi-tape, or I'll say 2-tape. Okay, a 2-tape Turing machine. Example transition function will look something like this: delta Q0 A comma E. I'll say moves to the state Q1, replacing with X, Y, left and right. Okay, so let us just see to the diagram. So Q0, I'm in the state Q0. Okay, so I have 2 tape symbols, A, B, C, and let me say I have D, E, F. So the transition function means I'm the state Q0 and one tape, A is the current symbol, and the next tape, this is the second tape. Okay, so this is the second tape. And this is the first tape. This is the first tape. First tape, A is pointed to, and the second tape, the current pointer, its own read-write head. This is read-write head 1, this is read-write head 2. That points to the symbol E. Okay, now this gives to what transition? State is Q1. Now my control unit moves to Q1, fine. But how are the symbols? Okay, A is replaced with X and E is replaced with Y. Okay, so A is replaced with X. Okay, now with B, I have a C. Okay, A is replaced with X and E. Previously, I have a D here, and E is replaced with Y. Am I right? And I'll have F. Are you understanding? The first is the tape, A is replaced with X. In the second tape, E is replaced with Y. Okay. And let us consider the pointer. So previously, it was pointer was in head was in A. Now I move it to left. Okay. If I have a blank over here, now it goes here. The head is moved to left. And for the second tape, the head is, this is again for first tape movement, and this is for second tape movement. Okay. Second tape is moved to right. So previously I was in this E has got replaced to Y. Now I should move to F. So this is the equivalent diagrammatic schematic representation of the transition function example that we have seen. Okay, so this is the multi-tape example. So in problems, especially in non-deterministic problems, we will not be able to manage with a single tape. So we might require multiple tapes. And what is the equivalence? There is an equivalence theorem for single tape and multi-tape. Let us consider M as a single tape Turing machine. Okay, and let us consider M cap as multi-tape Turing machine. Okay, so how are they equivalent? Are they equivalent? Now the standard Turing machine can be simulated. So they are equivalent in power. Okay, what I'm trying to say this is they are equivalent in power. So standard Turing machine can be simulated or easily it can be converted. Only I have a multi-tape Turing machine. Can I use this multi-tape Turing machine for the problem that I've already solved or proven that it's solvable with a single tape Turing machine? Yes, you can do that. The vice versa is also true. I've solved a problem with single tape Turing, multi-tape Turing machine. Now I have only a single tape with me. Can I use the single tape Turing machine to implement the solution or the algorithm? Yes, you can do that. Okay, so what we are trying to say is they are equivalent in power. Okay, so standard Turing machine can be simulated by a multiple Turing machines, a multi-tape Turing machine, and the vice versa is also true. Multi-tape Turing machine also can be simulated by a standard Turing machine. Both are true. Now this is very easy for us. A standard Turing machine can be simulated. When I have multiple tapes, I will use only one tape. Okay, I have n number of tapes. I'll use only one tape. That means the multi-tape has been converted to a single tape scenario. I'll not use a remaining. I'll take one tape, I'll use it. Okay, so that is easy. The first one is easy. For the second one, how can I, in case I have implemented my solution using multi-tapes. Now, how can I simulate the same implementation using a single tape? So that for that, there are something called as tracks, so similar to our audio track or in the tape we can have multiple tracks, or I can use a single tape also to represent with ending symbols, special symbols I can have. So let me have, I have like this. So 2 tapes I have. Okay. This is what I've implemented. Now I don't have multiple tapes anymore. I am in a situation to implement the same using single tape. So I have a single tape. There are 2 variants. This is a control unit. I'm in state Q. The one variant is I'll have different tracks. Okay. The same tape. Again, this is a single tape. Okay. This is a single tape. I have different tracks. So what I'll do is I'll say A, B, C, D. The first track and the third track will be the same as your tape. So E, F, G, H. Now can you see the first its head points to B, right? So the second track will be used for pointing. So I'll say 0, 1, 0, 0. Okay, the second track will tell me where the pointer for the first input tape, where the header for the first input tape is residing. And similarly, the fourth track will be used as a pointer for the second tape. Okay, this is like multi-track single tape. Okay, multi-track single tape implementation. So the header could be anywhere. I don't mind. I'll just use the zeros and ones to point to how to understand where the header is. Either we'll go for this, or there is one other implementation, which is I'll have a single track, single tape situation. Where I'll have multiple, 2 symbols I'll have. I'll use a hash to denote end of tape, say A, B, C, D. Then I'll have a hash to denote like end of this is tape 1, to make sure that this is tape 1. To denote it, I'll use a special symbol hash. So hash should not occur in your string anywhere. Okay, so that's a special symbol. Okay, so this is tape 2 content. Okay, tape 1 content and tape 2 content are separated with hash. Fine, okay. But where is my pointer? Okay, I'll use another special symbol called asterisk. Okay, to point to the current location. So both asterisk and hash should not be part of. So both asterisk comma hash are special symbols. Why do I use this special symbol? To convert a multi-tape to single tape problem. Okay, I've converted a multi-tape Turing machine to a single tape Turing machine. So I use special symbols to demarcate to just separate the tapes of both the, to separate n number of tapes, I use hash. And to represent the header position in each of the tape, I use the symbol asterisk. So both are special symbols. Hash and asterisk are special symbols, and they should not be part of input string. They should not be part of input string. Okay. So this is how we simulate a multi-tape with a single tape. Okay. So this is the equivalence. Both are same in power. All strings accepted by single tape machine will also be accepted by multiple tape machine, and the vice versa is also true. There's nothing in power, just in terms of implementation. With the environment that I have, when I have to implement, I can choose either one of them. Okay, power is the same. So what we have seen till now, we have seen an example on Turing machine. We have seen one variant called multi-tape Turing machine. So we have understood the transition function for multi-tape Turing machine. And we have also seen that single tape and multi-tape both are equivalent in power. Any computation done with single tape can be done with multi-tape also. Any string that is accepted by single tape can be accepted by multi-tape also. And the vice versa for both acceptance and computation also is the same. They are equal in power.